Let's do another example of finding a confidence interval. This time, let's try to find a 97% confidence interval for the average of the mean. And going back to, this is the same problem that we're working on in the previous video, but if this is the first time you're tuning into it, in this case, our sample mean was x bar is equal to 1076. The mean score for the SAT scores for a sample population, and we had our sigma divided by the square root of n came out to be approximately 3.16, I believe. Yeah, 3.162, because our standard deviation was 200 and our sample size was 4,000. But these are all things you should be given if you're trying to find confidence levels. You need to know what is your sample mean, what's your population standard deviation, and what's your sample size. But then the only other component we need to figure out is, well, how do we find a specific confidence interval? That's kind of like figuring out what is Z star. And with 97%, you'll notice that is not in table C, but you could find it in various ways. But let's practice once again using table A to figure it out. And to recap, what you want to do if you're going to use table A is you want to do C plus 1 over 2, where C is your confidence level. So this would be 0.97 plus 1 over 2. And this will give you the Z score. Then we can use a Z table to figure out this percentage. So 0.97 plus 1 divided by 2 is going to be 0.985. And basically, it converts your central confidence interval into a cumulative probability. This cumulative probability, that's what table A does. So now we're going to use that in table A, which it says 0.985, and we have exactly right here, which would be 2.1, 0, 1, 2, 3, 4, 5, 6, 7. So 2.167. Oops, what did I just say? 2.17. Let me do that again. 1, 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So this would be our critical score. And now that we know that, we have everything we need to know to find the confidence interval for this example, which is given by, again, this formula. So let's plug everything in. So 1076 x bar plus or minus Z star 2.17 times sigma divided by the square root of n, which we got to be approximately 3.162. Again, our margin of error, which the last part asked for, would just be the product of those two. So 2.17 times 3.162. That's going to be 1076 plus or minus 6.86. And so our margin of error is 6.86. And our confidence interval, we could either write it that way, or again, we could express it using interval notation. Let's go ahead and do that, which would be about 1082.9, and the lesser end would be the same thing but subtracted, which would be 1069.1. And so now we've finished all that. Let's go back to the packet, which is somewhere. There we go. Scroll out. So we determined our 97% confidence interval, which was 1069.1 to 1082.9. And now, just to sort of summarize, looking at all of these three cases, notice that a higher percentage confidence interval is actually wider. And this might seem a little confusing or like counterintuitive, but to have more confidence, we need to expand the range. Because, again, at the end of the day, we're not really sure how close this mean of 1076 would be to the actual SAT average of all students in Ohio, because we only know the average of those 4,000 students. But based on the standard deviation, we can figure out our confidence, and to be more confident, we need to expand our range, because we need to accept the fact that this is not probably exactly right. So like an 80% confidence interval, notice it's a little tighter because we're less sure about it. And sometimes you want a smaller interval, which just means you need to be less confident in that. But if you want to be more confident, you need a wider interval to encompass the probability that this is not on target. And a lot of times 95% confidence is good enough for a lot of purposes, but sometimes you want to be 99% certain this is right. Or even further, you could expand it more and more and more by altering your standard deviation by, multiplying by a higher z star score, aka critical value. And the margin of error in each of these, kind of going back and checking in on that, the margin of error for our 80% confidence interval, that was 1.29 times the standard deviation. Let's just analyze those real quick. It was about 4.1 for that margin of error, which means plus or minus 4.1. It's a fairly tight, not super bad. For 95%, that was just twice the standard deviation as an approximation. That margin of error was about 6.32 to get that confident. So again, more confidence means larger margin of error. And then with 97%, we just found that out to be up here, which was the calculation we just did a second ago, and now I've lost track of it. It was 6.86, or about 6.9 if we're trying to round them all. No. But again, notice higher percentage confidence intervals create larger margin of error, and they create wider intervals. And tighter intervals have lower margin of error, but we're less confident in those being good. And let's wrap this up by talking about the behavior of confidence intervals. Another question is, let's say we want to minimize our margin of error, answer particular questions about, essentially, if we want to know how good our prediction is, what are the ways in which we could reduce the margin of error in the way we're calculating our mean. But looking at the formula for the margin of error, one thing is we could reduce our confidence. Like if we're less confident in our results, we could have a smaller margin of error in our answer. Like I was saying, a smaller interval means less confidence. Another thing is to change sigma, the standard deviation of the population. We could reduce that. Basically the sigma describes the standard deviation of the population in question. Usually you can't change that, right? We're trying to study that. It's not something that we can actually affect. But if you do have a population that is more homogeneous, that has a smaller standard deviation, it will produce less margin of error because it's closer together. And lastly, we could increase n, the sample size, basically mean take more data points. The more data points we get, the more confidence we can be in our prediction. And that's just another kind of basic thing, like going back to the law of large numbers. The more and more samples we take, the closer it will be to the actual mean, summarized by this calculation.